there? You got it?
Yep.
No, sir.
Will you shut that back door for me, McLean? Okay, we're on page 89. We're talking about space-based astronomy. Doing astronomy from outer space.
Did you say today's the last day of lecture? Or am I?
Last day of lecture before the next test.
Benchmark lab, or whatever, and then
Stromberdy.
Stromberdy.
That's right.
Correcto mundo.
So, here's a problem. The atmosphere blocks a lot of the radiation that's coming in. Radio waves and visible light pass through the atmosphere relatively well. What we say is there are windows of radiation. There are windows, openings where radiation can pass. And because of the makeup of the atmosphere, radio waves and visible light goes through the atmosphere very well. Infrared does not. Ultraviolet does not. X-rays do not, and gamma rays do not. None of those penetrate the atmosphere very well at all. So if you're going to look at something using those rays, you need to find ways to get above the atmosphere. And one way to do it is to use a large balloon and float the telescope up. And here's a big telescope. You can see it's pretty darn big. There's a guy right there. But they use this balloon to float the telescope up way high up in the atmosphere. And those balloons will go all the way up to almost the very top of the atmosphere. So you'll have very little atmosphere in between the object and the scope. Of course, now you've got the problem of having the scope attached to a balloon, which could go anywhere, wherever the wind blows it. And so that's got to land somewhere, and you could imagine there's problems associated with it. That's a lot cheaper than launching something into space, which is another thing they can do. Put the telescope on a rocket and fly the rocket up into orbit around the Earth, and then drop off the scope, and your scope will be in orbit around the Earth. If you get it going the right speed, it'll just maintain that orbit for many, many years. Not forever, because there's even up in space, there's a few molecules. Our atmosphere extends out. It gets really thin, but it does extend out from the Earth for quite a way. And those molecules will eventually slow down the craft enough where it falls back to the Earth. Unless you go into a real high orbit. High orbits far away from the Earth don't decay as fast as orbits that are close to the Earth. But anyway, at least you'll have your scope above the atmosphere for a number of years, and you can take a lot of good pictures. And that's what a lot of those things are doing. The Hubble, spy satellites have cameras on them that look at the Earth. But there's a lot of satellites that have cameras on them that look into space. Again, it's expensive to do. Usually $200 or $300 million to launch a satellite up there. Could be more than that. This is an infrared scope that is on the top of a very high mountain in the desert somewhere. And it can sense infrared radiation, but infrared radiation doesn't travel very well through the atmosphere. So it does get a picture, but it's not that great of a picture. It's that's a big thing. You can see there's a vehicle right there, so that's a pretty darn big scope. The infrared scopes have a problem of the heat of the building messing with the picture in the scope, because you're getting radiation coming into that scope that's very faint. And so if the scope itself is hot, you'll get like static. You won't be able to see what you're looking at. You'll be getting glare from the hot scope. So what they do is they take these infrared scopes and they cool them down to almost absolute zero. So there's no heat coming off the scope itself, so you can just see the faint, like infrared rays coming to the scope. You can imagine it's probably expensive to cool a big telescope down to near absolute zero. So that's part of their operating costs. That's a good question. I'm not exactly sure. This is a picture using visible light of a valley somewhere in California, I think. And here's a picture on the right using infrared. So, see the eye there? So infrared can be useful. Have you ever seen those infrared goggles that soldiers use?
Border patrols.
They're sensing the heat. And it works at night, too. So infrared is very useful. Everything's giving off some heat. That desk is giving off some heat. My body's giving off more heat than the desk. So I would appear brighter to an infrared scope than the desk would. Here's a visible light picture of outer space, and here's the same picture with infrared. All this cloudy stuff, it looks like the infrared cuts through it a little bit. Interesting.
Bless you.
That's pretty cool, isn't it?
Bless you again.
Thank you.
This is a picture taken with the Spitzer space telescope. It's an infrared scope, now in an Earth-trailing orbit around the Sun. So here you have the Earth. We have a scope up there with the Earth is going around and around the Sun. Pretend the podium's the Sun. We launched this telescope that kind of sits behind the Earth and follows the Earth. Here's the scope. It kind of follows the Earth in its orbit, you see. And it's really far away from the Earth, and it will take some good pictures of outer space, and it doesn't have to worry about the atmosphere. So we got good pictures there. That's called the Spitzer Space Telescope. It was a NASA project. Here's a visible light image of Orion. Do you know Orion? There's Orion's belt and Orion's sword. And that's how it looks to the naked eye. That's visible. And this is how it would look in infrared. There's a lot of hot gas clouds that aren't giving off enough radiation to see, but they are giving off radiation that an infrared scope can see. So again, the infrared is very useful. We wouldn't even known that's there if we'd have never had an infrared scope. There's all these clouds of gas floating around in this area. Isn't that pretty? This shows them launching, I don't know what scope that is. If that's the Spitzer, it's some telescope being launched from the space shuttle. The space shuttle is good at carrying things up there and launching them. Of course, the space shuttles aren't being used anymore. Did y'all know that? They retired the space shuttles. They're just too expensive to run.
What are they using instead?
Nothing. Well, they can launch satellites up there with rockets, but they don't have anything that men go up on. All the rocket launch satellites are remote controlled. So we don't have any manned space vehicles right now. If we want to go up to the space station, which is partly ours, a big part of that is ours because we paid a lot of money for it, we hitch a ride on the Russian rockets. We don't have any manned space. Of course, the space shuttle is going to soon be replaced by something. They just hadn't figured out what. There's a lot of private companies that are going into that industry. Have y'all ever heard about that? The SpaceX and all that stuff? Y'all keep up with that at all? There's a billionaire named Richard Branson that has a company that's building spaceships. And you can hire them, and they even have flown some people up into low orbit and back. Interesting stuff.
Is it expensive?
It's expensive, yeah, but it's a lot cheaper than it would be to go with NASA. And he's trying to get it where where they can take tourists up there who want to pay. And I think they want to get it where it'll cost you about $200,000 or $300,000 to go into outer space on his ship. And there's people lined up to do it. So
They're just gonna throw up the whole time because it feels like.
Yeah, would you have to ride on that big spaceship thing first?
to get used to it, yeah, probably so.
I want to just sit there and throw up nonstop.
Yeah, you can do that too. You can just throw up.
Quit hating.
Yeah, not $3,000.
These are pictures. This is a picture taken with in the ultraviolet. On the left here, that's what that is. It's a supernova remnant. A supernova is a giant explosion, and that's what's left of it. And that's seen with an ultraviolet camera. And ultraviolet is another thing you have to be in outer space to see. The release of energy was enormous, and the afterglow lingered for millennia. The glowing field of debris shown here within the telescope's circular field of view lies 1,500 light years from Earth. Based on the velocity of the outflowing debris, astronomers estimate that the explosion itself must have occurred 12,000 years ago. That's this. This picture here, this false color image of the spiral galaxy M81 made by the Galaxy Evolution Explorer satellite launched into orbit in 2003 reveals stars forming in the blue arms well away from the galaxy's center. That's another galaxy far away, seen with an ultraviolet telescope. That's the sun seen in ultraviolet. Isn't that a cool picture? Everywhere where it's bright colored is lots of ultraviolet rays coming off the sun. And this is the stuff that burns your skin, gives you a sunburn. Ultraviolet. This is how an X-ray scope works. Do y'all know that X-rays are so high energy they'll penetrate things? You know, X-rays will go right through your arm, for instance, and that's how they get a picture. Well, you can't just have a mirror that bounces off X-rays, because the X-rays will go right through the mirror. But X-rays can be slightly deflected. So the way they focus X-rays is to have a series of mirrors, each slightly deflecting the X-ray. So you have a mirror here that just slightly deflects it, and a mirror here that slightly deflects it even more, and several of these are put together, and eventually the X-rays are focused. And so they're kind of in a curved fashion like this. So an X-ray telescope looks like a missile with several mirrors set up to deflect the X-rays to a point. If you just had one mirror trying to deflect the X-rays, it would just go through it. But many mirrors can get the job done. That's part of the middle of an X-ray telescope as it's being built. And here's an X-ray telescope right here. This is the vehicle that's launching it. See how it's long and tubular? There's a real big X-ray telescope right there. Look at this guy down here working on it. You can see it's big. Does it look expensive? Keep in mind they have to launch that in outer space because the X-rays don't make it far through the atmosphere. Sounds expensive to me. Let's see what this is. I'm not sure what this is. Oh, it's not letting me see what it is. That's a supernova seen in X-rays, I think. False color Chandra X-ray image of the supernova remnant Cassiopeia A. So there was a star at the center here that blew up, and the explosion is moving outward really fast at such high temperatures that it's producing a lot of X-rays. So that's seen with an X-ray scope. If you're picking up X-rays from something, you know it's really, really hot. X-rays only come from something that's extremely hot. A debris field of scattered hot gases that were once part of a massive star. The red, green, and blue regions show different intensities of X-rays and also different abundances of heavy metals. Roughly 10,000 light years from Earth and barely visible in the optical part of the spectrum, Cassiopeia A is awash in brilliantly glowing X-rays spread across some 10 light years. Wow. It's another X-ray image of some kind of explosion. This shows an X-ray image of the sun at different times in its cycle. The sun goes through a cycle where sometimes it's quiet and is not releasing many X-rays, and sometimes it's hot and is releasing a lot of X-rays. And we'll study that cycle when we get to the sun. Right now the sun looks more like this. It's in a bright part of its cycle. Somewhere up here, one of these.
How often does it go through the cycle?
The cycle is an 11-year cycle. I think this is 11 pictures. 1, 2, 3, 8, 9, 10, 12 pictures. It's an 11-year cycle. There's an X-ray telescope being launched from the space shuttle. Now, gamma rays are so penetrative that they can't even hardly be deflected by a mirror. So you can never make a nice image there's no such thing as a gamma ray telescope. You can't even deflect gamma rays. The only thing you can do is detect them, and there are gamma ray detectors, but they can't give you a sharp, crisp image. So this is a gamma ray detector that's bright here. That means it can tell you the general direction that gamma rays are coming from. It's getting a lot of gamma rays from something in this area, but it can't give you a good picture of it. And so what they do is they have these gamma ray detectors that can say, oh, we're getting a lot of gamma rays coming from this direction, and then they point a telescope at it and see if they can see what's going on, like an X-ray scope or a regular visible scope, and see if they see something happening there. And what they found out is that gamma rays are produced only in supernovas, huge explosions of stars that happen when a very large star dies. So these scopes, infrared, ultraviolet, X-ray, and gamma ray, all those detectors and scopes have to be in outer space, or on a very high mountain, or on a balloon, or something that gets rid of the atmosphere, because they don't make it through the atmosphere very well. Only radio and visible go through the atmosphere very well. So those can be on the ground. Radio and visible scopes. That's a big explosion and some satellite seeing it. It's an artist drawing, it's not real. I thought it was a cool drawing, so I threw it in there. Eliza, do you think that's cool?
It's pretty cool.
This is what the sky looks like in radio waves, infrared, visible, X-ray, and gamma ray.
So how could they get the picture of that gamma?
Just using the detectors, seeing where the detectors are picking things up, and plugging all that into a computer.
Oh, so that.
Yeah, that's a composite of lots of data.
So we don't have any like gamma rays on planet Earth.
No.
We have detectors to see like where they are in the
And any detectors we have are up in space.
No, we don't have any on Earth either.
Now, well, you're not going to get anything because the gamma rays won't make it through the atmosphere. The only time we ever produce gamma rays on Earth is in a nuclear bomb. And then they'll travel about 2 miles from the explosion and then they stop. They won't go very far through the atmosphere. You think 2 miles is a lot. It's a lot to us, but it's not a lot compared to the size of the Earth. It's very, very short.
Or is there a nuclear bomb that could potentially take out like the whole United States? Like
One bomb?
Yeah.
No. But to make sure that we could do that if we wanted to, we have thousands of bombs. So we could take out the whole world if we placed one in the right spot. That was they kept stockpiling those in the 70s and 80s, 60s, 70s, and 80s. And now they're trying to reduce the number of them because it's just kind of crazy. They're also scared a terrorist might get a hold of one. If a terrorist set off a nuclear bomb in the middle of New York City, it'd blow up the whole city. Like I say, it only goes a few miles, but the city's only a few miles, you know? You could blow up half of St. Simon's with one bomb if you got one. So they're kind of worried about that, so they don't want to have so many of them, so they're trying to reduce the number of nuclear bombs.
Doesn't the radiation like linger? And
It lingers.
Does it go farther than the explosion itself?
Yeah, probably so. But the lingering is a problem.
Doesn't that kill like more things?
Yeah, it'll last. The radiation, the place will stay irradiated for a long period of time. I think it's up to hundreds or thousands of years.
Oh my gosh.
So nothing could live in that area for a real long amount of time.
Like Chernobyl with the radiation.
Like Chernobyl, yeah, nobody will be there.
The radiation's supposed to be gone kind of soon though.
Nah,
You can go there if you wear like a suit.
that was just in that movie. Yeah, if you wear a suit, but that's to protect you from the radiation.
They said, someone told me that. It should
Really?
be covered.
Nah, it's still going.
How long ago was that?
70s.
How long is the last, did you say?
Well, it depends. I mean, the radiation will be around for hundreds of thousands of years, but how long is it dangerous to people? That's a good question.
They said like
I mean, you might be able to go there and stay for a few minutes, but to live there and drink the water and stuff like that and eat crops that are grown there, that's probably dangerous long term. So a place probably won't be able to be inhabited for many hundreds or even thousands of years. Last night, those that were with me, I showed them the Milky Way. You remember the Milky Way?
Mm-hmm.
That's a visible picture of it if you have a good camera and a long exposure time. This light going across the sky. Okay, well, I want to continue with this video about telescopes that we were watching. You can turn that off now. And